Okay, you can apply total runout to a tangent plane. So tangent to one surface or multiple coplanar surfaces, the number noted when more than one surface is in the requirement, and the extent of the distance from the axis of rotation to the furthest point on tolerance surfaces, and then make sure the profile tolerance to control the tangent plane for all features is relative to the datum axis. Okay, so what happens when we have combined effects of size and runout tolerances? Now, the runout tolerances may be larger than the size tolerance, or consequently, the size tolerance may be larger than the runout tolerance. And then the runout variation may occur on a perfect form feature, and then features must meet both size and runout requirements. Okay, so they don't have to meet them independently. They have to meet them independently, but not together is what that means. Now, let's look at this case here. We've got a common datum, and then we have a relatively small tolerance here of plus or minus 5 thousandths on the size, and then we have a 15 thousandths runout. So what does this mean? Okay, so we have a perfect cylinder eccentrics to the axis here, like that, and this comes allowed to come out 7.5. That gives us our full indicator movement of 15. So that's how we can meet the size tolerance and a larger runout tolerance. Now, what happens if you have a large size tolerance and a small runout tolerance? That's what we got here. We got plus or minus 10, and then we got a less than that. Okay, so what we have here is the MMC boundary sticks out right in here, and then we scan our indicator back and forth. Okay, and then finally, the runout of an assembly. In a lot of cases, like in machine design, for instance, you have a motor, and the motor is going to be fitted with a pulley, and then you need to align that pulley precisely to something else, or if you had a coupler or something like that. Well, what you would need to do is to take the overall assembly of this and put a runout tolerance on the overall assembly. And that's kind of what they're trying to do with this one here, is they're trying to control runout of this pulley, if you will, a sheave, relative to the datum surfaces here. So circular and total runouts may be applied on assemblies. Establishes a tolerance for requirements relative to an axis of rotation. In this case, the axis of rotation would be the axis of rotation of the electrical motor. And then the axis of rotation is constrained in rotational degrees of freedom relative to the datum reference frame. And reference datums do not constrain the translational degrees of freedom. So really what we're trying to do is to control the wobble, if you will, of this sheave to drive our uh, our power transmission system. Okay, so this concludes the movies for Runout. Thank you.